we basically solve that with polynomials and rational functions. We can just use direct substitution. However, you can't use direct substitution on any other types of functions. We're going to see. This brings in, when can we use direct substitution? When it's continuous. But what does it mean to be continuous? So you kind of looked at it in pre-calc and probably algebra. Right? And generally the notion is it's continuous if you can draw its graph without lifting up your pen. That's not the definition. We start by defining continuity at a point. Call it A. 3 conditions must be satisfied. First, f of A has to be defined. That's pretty obvious. Second, the limit has to exist. And finally, the limit has to be f of A. Any one of these 3 conditions are not satisfied, it is not continuous at that point, in which case we say it is discontinuous. Function is continuous from the right if the right-handed limit is f of A, continuous from the left if the left-handed limit is f of A. It's not on here, but if a function is continuous at every point in an interval, then we say it's continuous over the entire interval. Determining continuity of points should be pretty self-explanatory. You just have to make sure all 3 of those conditions are satisfied. First and easiest one is to make sure that f of A is defined. Right? If it's not, you're done. It's not continuous. If it is, compute the limit as x approaches A. If that limit does not exist, it's not continuous at the point. But check one-handed continuity. And to also calculate left and right. If that limit does exist, check to see if it is f of A. If it's not continuous. If it is, then obviously it is continuous. Now, when are functions continuous? Polynomials, rationals, continuous over their entire domains. Right? That's not difficult to prove. We discussed the types of discontinuities as well, right? We're also going to now define them formally. We Removable if the limit exists but is not equal to f of a. To jump discontinuity, if the one-sided limits exist but are not equal. And infinite, obviously, if one of the one-sided limits is infinite. Yes.
The graphs like 1 over x or tangent x is like both a jump and infinite discontinuity.
It would not be a jump. So jumps, the limits, the one-sided limits have to exist.
Okay, so infinity counts as non-existing.
If it's infinite, doesn't exist. We just use infinite to give us a better explanation of what's going on.
Okay, thank you.
Here's the big one. The composite function theorem. If f of x is continuous at L, and the limit as x approaches a of g of x is equal to L, then the limit as x approaches a of f of g of x is f of the limit of g of x, which is f of L. This theorem is what will allow us to use direct substitution for any continuous function. As an example, if I ask you for the limit as x approaches pi of cosine of x, the limit of x is pi. Is cosine continuous at pi? Yeah. So your limit's cosine of pi, which is -1. Trig functions continuous over their entire domains. This is also a pretty important theorem. In general, any theorem that actually has a name is very important. So composite function theorem. Intermediate value theorem. Let f be continuous over a closed bounded interval a to b. If z is any number between f of a and f of b, then there is a number c in that interval such that f of c is equal to z. Right, what this is saying is you have a continuous function over an interval a to b, then that function has to take on every single value between f of a and f of b. Which again makes sense, right? To be continuous, you're not lifting up your pen. So you're going to have to cover every single value between f of a and f of b. Graphically, this is what it's saying. Right, that blue part is the intermediate value theorem. I can't remember if that's actually proven in the book or not. I don't think it is yet, because you need the actual definition of a limit. But generally speaking, if you have an obvious statement, like that one, it's going to be really hard to prove. The more obvious it is, the harder it is to prove, generally speaking. We're given a piecewise function. We're asked, is it continuous at x equals 1? If not, what kind of discontinuity is at that point? I think I'll go a step further and ask, is it continuous everywhere?
Yeah.
Right. Well, 2 is clearly continuous. So that's fine. X squared minus 1 over x minus 1. Well, that's a rational, right? So it's continuous everywhere over its domain. X can't be 1. Oh, well, that piece has x. X cannot be 1. So that's continuous everywhere within its domain. The only possible point of discontinuity is that break in the piece, right? In this case, it's 1. So that's what we're going to check. Is it continuous or not? We don't know. We have to look. First, is f of a defined? So is f of 1 defined? Yeah, what is it?
2.
First condition satisfied. The second condition is, does the limit exist? So check the one-sided limits. Limit from the left. Actually, I don't think I even need to do left or right-handed limits in this case. But I will anyway. If we're approaching 1 from the left, which piece is it?
The bottom piece.
Why do you say bottom?
The function is equal to 2 at the whole time except at x equals 1.
Is that what that's saying?
I'm simply pretending. I don't know.
You said top. I heard the top over here.
Oh no,
Why?
I misread. I'm sorry.
I mean, I assume because equations move left and right, so it'd also be top to bottom. It was just an assumption.
No, it's the opposite of what I said. I misread. That's my fault.
So we're approaching 1 from the left. So yes, all the values are less than 1. But I don't see an x less than 1. But remember, at a limit, you're not at 1, are you? So that means x doesn't equal 1, which is the first piece. Which is why I said I don't really think I need the one-sided limits in this case. It's a rational function, direct substitution. Well, that gives 0 over 0. Which means we have to do algebra. What's x squared minus 1? What's that factor to?
It's just 1. It's minus 1.
Right here by the school.
So isn't that what you'll be left with? What's that limit? 2. Now you need the right-handed limit. Same argument. limit is 2, which means the limit exists. Oh. But that equals f1. You said f1 is 2, right?
Yeah.
All 3 conditions are satisfied. It's continuous at 1. Which means we don't need to identify the type of discontinuity because it's not a discontinuity. Which, by the way, means that this function will be continuous everywhere. G of 1, is it defined?
Yes.
What is it?
1.
Check to see if the limit exists. Left-handed limit. What piece?
It's the parabola, is that squared?
Why?
Because x is less than 1.
Approaching from the left, values are less than 1, right? What's that limit?
1.
Right-handed limit. What piece?
The bottom.
Why? Right, we're to the right of 1, so all the values are larger. What's that limit?
So 1.
Does the limit exist?
Yeah.
What does it equal? Oh. Wasn't that what we said G of 1 was? Or- That one looks kind of angry. Okay. It's continuous at 1. Find values of k that would make this function continuous at 2. And then determine what that limit is. So remember, there has to be 3 conditions satisfied. G of 2 has to equal k, and it has to exist. Right, so we know right away k is going to have to be a real number. Okay, well that's good. That condition is checked off. The limit has to exist at 2. This is a not equals and an equals. So I can just look at the limit as x approaches 2 right off the bat. Direct substitution yields indeterminate. Right, but using algebra, you'll wind up with that being the same as the limit as x approaches 2 of x plus 2, which is what? 4. Okay, well that is satisfied regardless of our value of k. So we don't have to worry about that. And then the third condition. How do I do G? F of 2 has to be that limit. Which means k has to equal 4. That's not okay. We already found the limit, so there's the limit.
To be honest, I'm lost. I don't understand this.
So definitely in continuity. Those three conditions have to be satisfied. So that's what I checked. Right? G of 1 has to, or no, sorry, F of 1 has to, F of 2 has to exist. What's F of 2? K, right? But K is any real number, so clearly that exists. The limit has to exist. Limit's 4. That exists. Excellent. Third and final condition, F of 2 has to equal the limit.
So,
F of 2 is K. That has to equal 4, so K has to be 4. Well, that's an easy one. Is this function continuous?
It's not.
Nope. Not continuous. Which condition does it fail?
2.
Limit doesn't exist. But do the one-sided limits exist?
Yes, but they're not the same.
What's the left-sided limit?
2.
What's the right-sided limit? What kind of continuity is it? Or discontinuity?
Jump.
Is this left-hand continuous or right-hand continuous?
Right hand?
Why?
Because it's greater than or equal to. I'm guessing. I'm
I'm
not
not sure
sure.
why.
Okay.
right-handed limit is equal to f of 0, right? I think it's right-hand continuous. T of 0. Which means it's right-hand continuous at 0.
So if the right-hand side equals f of a, it's right.
If the right-handed limit is f of a, then it's right-hand continuous. If the left-handed limit is f of a, it's left-hand continuous.
So if it were to be x is less than or equal to 0 instead.
For this specific example, it'd be
Yeah.
left-hand continuous. Is sine of the square root of x plus 1 continuous at x equals 0? You need to justify your answer. The rule for sine. Sine is continuous everywhere, right? Or continuous over its entire domain. But in this case, we're taking sine of a square root. So look at the square root of x plus 1. But they didn't give us a rule for that one. But they did give us a rule for x plus 1. Right, so x plus 1 is a polynomial, it's continuous everywhere. Which means that x plus 1 will be continuous specifically at x equals 0. In fact, square root is going to be continuous over its domain as well. So root right is root x will be continuous for x greater than or equal to 0, right? What's the rule? So what happens to the domain if you shift a function?
Like it moves back one. Like over the x axis.
Is it always back?
Like if it's underneath the square root, it goes back.
Right, so underneath, so if it's actually inside the function, you're definitely shifting the domain, right? If it's outside the function, the domain remains unchanged. So what kind of shift is this? Well, what do you mean by back?
You mean transformation?
Right, there's three transformations. This is shifting or translation. Can't say back. Back is for the third dimension, which we're not
Like,
at right now. It's to the left. And so your entire domain shifts left 1 unit. Oh. X is larger than -1, so we're continuous at 0. And then, of course, sine of x is continuous everywhere because that's its domain. That means sine of root x would be continuous whenever root x is continuous. Right, then that previous argument, root x plus 1 is continuous for x being equal to -1, and we have our answer. Show that there exists a c in 0 to 1 where cosine of c is equal to c.
Is that true?
It says to show it. So let phi of x be cosine of x minus x.
What is that symbol?
That's the Greek letter phi, lowercase phi.
Wait, does that matter?
No, I'm just using phi of x. Maybe my second or third favorite Greek letter. We now want to show there exists a C in 0 to 1 such that, sorry, not, phi of C is equal to 0. Because that would be the same thing as saying cosine of C minus C is equal to 0. First, phi of x, isn't that continuous on that interval? That should be continuous everywhere. Right? Cosine is continuous everywhere, x is continuous everywhere. So their difference would be continuous everywhere. What's phi of 0?
One.
What's phi of 1?
-1. No. Yeah, isn't that
It's cosine of 1 minus 1. What's cosine of 1?
0?
No.
No, I'm saying the answer is 0. No. Am I?
One is greater than 0. If we look at phi of 1, well, cosine of 1 doesn't 1 fall between 0 and pi over 2, which is the first quadrant. That means that cosine of 1 is going to be positive, but less than 1. That makes cosine of 1 minus 1 negative. Which makes 0 between phi of 1 and phi of 0. Intermediate value theorem says a C has to exist, where phi of C is equal to 0. Right. We showed phi of x is continuous on 0 to 1, which means it has to take on every single value between phi of 1 and phi of 0, your two endpoints. And we also showed that 0 is in between those two values. So that's the intermediate value theorem. We know such a C exists.
So why did you do cosine of x minus x?
Because that's the function I want.
Like, is it?
Because what we want to show, cosine of C is equal to C. Which means cosine of C minus C has to be 0.
Yeah, so you
Oh,
get equal
okay.
0.
Right. So that's my function of x. So we want to show that phi of x is 0. Notice what the intermediate value theorem does not tell us. it does not tell us what C is equal to. It's simply guaranteeing there is a number between 0 and 1 where cosine of that number is equal to that number. It just doesn't tell us what that number actually is. And with the tools we currently have, it's impossible to find that number. Have no fear. By the end of this semester, we'll be able to guess what that number is pretty accurately too. If I remember, maybe I'll revisit this, find what that C is. So here's Q of X. We're being asked if we can define Q of 0 to make Q continuous at 0. Right, so right now, obviously at 0 is undefined. Right, the question is, can we choose a value for Q of 0 to make it continuous? Now remember, 3 rules to be continuous. Q of 0 has to exist. That's what we want. The limit has to exist, and they have to be equal. So let's find that limit. Next, here's the idea. Can we define that function?
You multiply the top and bottom by square root x minus 4 plus 4 plus 4 plus 2.
The numerator would become x plus 4 minus 4.
You cancel it out.
Which is just x. There's Q of 0. So just define Q of 0 real quick. R of x is now continuous. We want to make that function continuous at pi over 2. Well, keep in mind that k is a real number. F of pi over 2. What would that equal?
Cos of pi over 2 plus k.
K is a real number, so that's going to exist. So that's good. Now let's take a look at their limits. Approach pi over 2 from the left. What piece do we need?
Sine. Sine theta.
I don't know why I'm using x. Is sine continuous at pi over 2?
Yeah.
Yes. This limit then is just sine of pi over 2. Which equals what?
Here.
Isn't root 2 over 2? Oh,
It's 1. Pi over 4 is root 2 over 2. Now from the right. Which piece is it?
Cos of theta plus k.
Oops.
H of theta or?
F. Limit of theta plus k as theta approaches pi over 2 from the right is what?
0 plus k.
Okay. Oh, cosine k?
So theta plus k as theta approaches pi over 2 from the right. Overthinking it. Just pi over 2 plus k, right? Is cosine continuous there? Yes. Composite function theorem says we can just pull the limit inside. those two one-sided limits must equal to be continuous at pi over 2.
Then k needs to be negative pi over 2.
So cosine pi over 2 plus k has to be 1. Where does cosine equal 1?
0.
Where else?
Pi.
Cosine pi would be minus 1.
And 2 pi.
Where else?
0, 2 pi.
Where else?
6
Where else?
infinite pi. Infinite pi total.
What's the condition?
Oh, is it infinity?
There's an infinite number of values,
Yeah.
but all those values have something in common,
It's a full rotation.
which means it's what?
360.
What about 360?
Is it because it's on the x-axis?
Yeah, so how do they have to relate to 360 degrees? So what does it mean to be coterminal? Do you remember that?
Yeah,
What's the definition of coterminal angles?
it's like the same angle if you go all the way around it. Like
But what's one full revolution?
2 pi.
So you would just, what, add 2 pi or subtract 2 pi to get a coterminal? Or any multiple of 2 pi. Right, because 2 pi would just be one revolution, but that's not the only coterminal angle. 32 pi would also be coterminal.
What does that mean?
Pi over 2 plus k has to be 2n pi, where n is any integer. So I'm saying that pi over 2 plus k has to be a multiple of 2 pi. So then what's k?
All the numbers.
2n pi minus pi.
K would have to be any angle coterminal to negative pi over 2. Which is why I wrote it that way. There's an infinite number of values for K, but they all have to be coterminal with negative pi over 2. And so I'll say, yeah, we'll write it that way. Those are all the values of K that would make this function continuous. And the instructions did say values, value or values, so it didn't ask for one value. So you have to actually list them all. And that listed them all.
Why does it start off with negative?
Because pi over 2 plus K has to be a multiple of 2 pi. So subtract pi over 2 from both sides. And I just wrote it in that format, because that's the standard format for coterminal angles.
Yeah, for sure.
This is why I love trig. Trig is awesome. What else do we have? Any other interesting ones? Actually, we do. Designer. We'll make that function continuous at 4. Does f of 4 exist?
Yes.
What does it equal?
7.
Four from the left. Approach 4 from the left. What piece is it?
E raised to K times X.
What's the domain for the exponential function?
All real numbers.
All real numbers. What's the limit of kx as x approaches 4 from the left?
E to the 4K.
I'm not looking for that yet.
Oh.
Just kx. What's that limit? You said it. Okay, right?
Okay. Yeah.
But k is going to be a real number. So that makes 4k a real number, right? Is e continuous there? Yes. So the limit's e to the 4k. limit as x approaches 4 from the right. So what piece do we have to use now?
The bottom piece.
And what's that limit?
7.
Oh, good, that actually equals f of 4, so that's good news. This means that e to the 4k has to equal 7, because the two limits have to equal for the limit to exist. How would you solve that for k?
Do the logarithm.
Which one?
It would be ln of, yeah, it'd be ln of 7 equals 4k.
What's k?
Ln of 7 divided by 4.
You know what? I don't like that form. Give it to me as the log of a number. Your calculator won't help you here. Because I don't want an approximation.
7 4 1 3/4.
Would you just replace ln with 1/16?
Do the same thing.
So what are you asking?
I want this as the natural log of a single number.
This is just yes, but L and 7 minus e to the 4.
I know you're trying to do and use the wrong property.
Would be ln of 7 over 4.
You're on the right track using laws of logs. Wrong law.
Wait, does it bring it up? Wouldn't it be ln 7 minus ln 4? That's just simplifying. Is that simplifying? That's not simplifying.
Doesn't work that way.
Would you multiply the 4 to the others?
What do you need?
7.
What is it?
4 through 7.
Yes.
Okay.
It's natural log of the 4 through to 7. That's the power law. Natural log of 7 to the 1/4, which is the 4 through to 7.
What's ln 7? ln 7.
Right, it's natural log of 7 all over 4. That's why I didn't. Single value there. You are going to need to know your laws of logarithms for this course, specifically when we get to logarithmic differentiation. So if you're rusty on those, you have a little bit of time to review. Okay, good. I stretched that out long enough. Questions on continuity? I reiterate, the most important result from today is the composite function theorem. theorem that's going to allow us to just use direct substitution for any function. The section 2.2 homework was due today. But remember, you can still request an extension, which would be 25% deduction on all work submitted.
I tried to request an extension online yesterday, but it wouldn't let me.
Because it wasn't past due.
Oh, okay.
It won't let you do it until it's past due. So you should be able to do it now. And that penalty is not retroactive. So any work you submitted before will not be penalized. Only work submitted after will be penalized. The 2.4 homework, due a week from today. Don't forget the 2.3 homework is due Tuesday. And that's going to be out there for a while. First group assignment, don't forget. All right, so the rest of the class, work on this, and I think there's going to be a lot of the find the value that makes this continuous. Yeah, that's what it looks like. And there's some classifying. Oh, fun. There's 3 intermediate value theorem questions. That's exciting.